Good afternoon, everyone. Today I'm going to give a seminar on the topic string matching algorithm as part of our assignment for the course of Advanced Algorithms Analysis and Design. What is string matching? Whenever we are trying to search for a text, a word, or a letter in a text document, a file, or in the Google search engine or any other web search engine, we are using a string matching program. For example, in the find function like grep, we are utilizing this string matching algorithm. And many of these algorithms are created using the finite automata in order to effectively search for our string. This problem of string matching. Given a text T of length n and a pattern P of length m such that m is less than or equal to n and both are taken as arrays. Further, assume that the elements of the pattern P and the text T are characters drawn from some finite set of alphabets, sigma. Now for some S which is less than or which is greater than or equal to 0 and less than or equal to n minus m. That is the difference between the length of the text and the pattern. If the character in the text T of S plus J equal to the character in the pattern P of J for all J belonging to 1 to m, then P occurs in T with shift S. That is, that pattern P occurs in the text T with some value of shift S. That is the value of the S when the P has a match in the text T. And we call this value of S as a valid shift, otherwise S is declared as an invalid shift. In a string matching problem, our objective is to find all valid shifts with which a given pattern P occurs in a text T. There are many pattern matching algorithms. Here we are going to discuss the naive string matching algorithm, the Rabin-Karf algorithm, the string matching using finite automata, and finally the Knuth-Morris-Pratt algorithm, or just the KMP algorithm. In naive string matcher, it takes two inputs, the text and the pattern. Here, n is the length of the text and m is the length of the pattern. So for some s going into a loop from 0 to n minus m, we are specifying a condition, another loop, inner loop. If p of 1 to m, that is some character in the pattern, and matches equal to some character in the text T of S plus 1 to the length of the pattern S plus m. This is repeated until there is a match. Then print finally at the end of this print that and print pattern occurs with shift S at the end of the pattern, the length. So the worst case running time for this naive string matching algorithm is outer loop will run for n minus m times, so it will be n minus m plus 1, and inner loop which is m times, that is the length of the pattern. Its character in the pattern is compared with its character in the text, so it runs for m times, so totally it becomes to n minus m plus 1 into m. Base case is n minus m when the pattern occurs in the first loop itself. Consider an example for this algorithm, string matching algorithm. Here the text given is ACAABC, and the length of this n is 6 and the pattern is AAB, so m equal to 3. For s equal to 0 to n minus m, that is 6 minus 3 equal to 3 equal to 3, so p of 1 equal to, for the first shift, s equal to 0, t of s plus 1, that is t of 1. P of 1 is A and T of 1 is also A, so here is a match. Again we'll go to the next P of 2. P of 2 is equal to T of S plus 2, but P of 2 is A and C of 2 is C, hence there is no match. So we will go on the next loop, that is shift S1, and then here again we will compare the pattern with the text. P of 1 equal to T of S plus 1, and that is T of 2. Then in the first shift, so P of 1, C is not equal to A, hence again we will go to the second shift, that is S equal to 2, actually it's a third shift. And so as when S equal to 2, again P1 equal to T3 and P2 equal to T4 and P3 equal to T5, hence there is a match. But since we have to run for S, go on the loop for n minus m times, that is 3 times, so we will go again continue for S tends to 3. Here first value in the pattern is equal to the T of 4, T of 2, P of 2 is equal to not equal to T of 5, hence it is discarded. So finally the output will be pattern occurs at S equal to 2 and S equal to 2 is hence a valid shift. Others are invalid shift. Now the Miller-Rabin algorithm. Here, given the text T which is of length n and a pattern P of m, where length m is less than or equal to n, both are arrays. So it is similar to the knife algorithm, but here change is made only in the final set of alphabets for P and T. That is, here sigma is taken as decimal digits for its character. So here in this Rabin-Karp algorithm, the objective is finding all valid shifts with which a given pattern P occurs in a text T. Same objective. Here let us suppose that P denotes decimal value of given a pattern P 1 to m. That is, for the P of 1 to m, that specific character is here in Rabin-Karp algorithm, it denotes a decimal value. Similarly, T of S denotes a decimal value of length m substring T of S plus 1 to T of S plus m of the given text T of 1 to n for S equal to 0 up to n minus m. Now it is very obvious that T of S equal to P if and only if there is if the character in the text T of S plus 1 to S plus m equal to P of 1 to m. Thus, S is a valid shift if and only if the decimal value T of Ts in the text equal to the decimal value P in the pattern. Now the question is how to compute P and Ts efficiently. The solution can be provided using the Horner's rule. As we all know that Horner's rule consists of provides a formula using a precondition and a postcondition. Here, in this example, we consider the number decimal digits 3, 4 and 5. Here, it can be constructed using 5 plus 10 using this formula, 5 plus 10, 4 plus 10 plus 8. Here, using this, finally we get 345. That is P equal to P of 3, the first higher order bit, plus 10 of P of 3 next higher order bit, plus 10 of the lower order bit. So from here we can derive the general formula for computing P in tan theta of m. The rule is P equal to P of m, that is the highest order bit, plus 10 of next higher order bit, plus 10 of next higher order bit, plus up to the last 10 of plus the last lower order bit. Similarly, T naught can be computed from T of 1 to m in time theta of m. To compute the T1, T2 of the T of n minus 1 in theta n minus m, it is observed that T of S1 can be computed from T of S in constant time. Consider a text 314152, T naught equal to 31415. Now we have to consider T1, that is T of s plus 1. Here m equal to 5 and SIF equal to 0. All the higher order bit is 3 and the higher lower order digit is 2 now. Here to construct this T1 we can use this formula T10 equal to this one, and here using this we can derive the general formula T of s plus 1 equal to 10 of Ts minus T of s plus 1 10 m minus 1 plus T of s plus m plus 1. This is based on Horner's rule. So hence the T of 1 can be summarized as equal from the formula as T of 1 equal to T10 of T naught, that is T s is T naught minus T of s plus 1 is 0 plus 1 T1 which is 1 into 10 to the power m is 5 minus 1 is 4 10 to the power 4 plus T of 0 plus s plus 0 5 is m plus 1, that is 10 T of 6, that is 2. Now T1, T2 and T up to T2 and m minus m will be in theta of n minus m. So we can summarize the above formula in words as subtract this like this 1 2 3 given here. The another issue in this computing this in this algorithm is that we may find that P and Ts may be too large to work effectively or conveniently. So fortunately, we can use a simple solution for that. That is compute P and Ts modulo a suitable modulus Q. Example: consider a window of length 5 as saddle, that is 31415, and numerical value of the window is 31415. Now consider the mode value Q as 13. So 31415 mode 13 equal to 7. Hence it reduces to 7. Thus we can use this algorithm to compute Ts plus 1 from Ts effectively. Spurious heat. Now we have to, after finding that the value mode, we have to check again, verify again, to see that whether it is just a spurious hit or whether it actually gives the desired Ts plus 1. Here for example, P equal to 31415, M equal to 5. Now 31415 equivalent to 7 mod 13. Hence it gives the right answer. Window begins at position 7, valid is equal to 6. As shown in here. Now generalizing the above is just generalizing the above algorithm. So here is the actual pseudocode for Rubin curve matcher. We take the text pattern, the T modulo O function and Q modulo Q function for the as input. Worst case running time is pre-processing time, it takes theta of m. Matching time, it takes n minus theta of n minus m plus 1 into m. Suppose if p equal to a to the power m, t equal to a to the power n, verification take time theta n minus m plus 1 m, since each of the n minus m plus 1 possible state is valid. If only there are few valid states and matching time of the algorithm is only order of n minus m plus 1 plus cm equal to order of n plus m. Next, the finite automata theory algorithm for string matching. We know that finite automaton M is a quintuple, that is, it consists of 5 tuples, Q as a finite set of states, Q node which belongs to Q is the start state, A which also belongs to Q is a distinguished set of accepting states, summation sigma is the finite input alphabet, delta is the transition function from the Cartesian product of the finite set of states and the input alphabet, finite input alphabet, called the transition function of m. String matching automata are very efficient because it examines its character exactly once, taking constant time. The matching time used after preprocessing the pattern to build the automaton is therefore theta of n. So are some of the properties of the finite automaton for string matching. Empty string is both a suffix and prefix of every string. For any string x and y and any character a, we have x. X is a equivalent a match just y if and only if xa does not match matches ya. Also, it can be proved that the true and are transitive relations. Suppose that here are the properties. Here is an example of the finite automata. Here is the transition table and the translate diagram. We have two states 0 and 1 and the two input symbols a and b. So here the transition table can be constructed seeing the state diagram. For string matching, an auxiliary function sigma called the suffix function is defined corresponding to the given pattern P. Function sigma is a mapping from the summation star, that is 0 to 1 up to m, such that summation sigma of x is length of the longest prefix of p, that is the suffix of x. That is sigma of x equal to maximum or max of k, such that pk is an input of x, is a suffix of x. The suffix function sigma is well defined since the empty string p not equal to empty is a suffix of every string. For a pattern p of length m, we have sigma of x equal to m if and only if p is a suffix of x. The string matching automata that corresponds to a given pattern p of 1 to m is defined as the state q from 0, 1 to m. The start state q naught is state 0 and state m is the only accepting state. The transition function delta is defined by the following equation. Delta of q on some input character a equal to sigma of pqa. The machine maintains as an invariant of its operation, so phi of ti n equal to sigma of di. Here is an example of the string matching automata for a given pattern. Pattern string is p equal to a b a b a c a. As towards right source matching, as towards is from. No as for some state, and so a match is found only when it reaches the accepting state. Here, for example, 0 to when there is a when on input symbol a, the starting state 0 goes to the next state 1. When on upon next next input b, again it's matching, so it goes to the next state. Upon on c, upon the next input a, again it is matching, so it goes to the next state. Upon the next input b, again it is matching, so upon b, again it is matching, it goes to the next state. And lastly, so when it is no match is found, it goes to the previous state from where the pattern can again be checked. Here is also an example given the text ABA, ABA and some pattern as given here, ABA, BACA. Now we are going to check if whether this pattern occurs in the text T. And here is the algorithm for the finite automaton matcher. It takes the text T, transition function delta, and the length of the pattern M. Here for considering the length of the text as n and the q as a starting state 0, for I equal to 1 to n, that is we are going to the loop, we are going to check the condition. If we get the state Q for the transition Q from in N and the transition Q of the pattern and Ti in the text. If Q equal to M, then print that the pattern occurs with shift I minus M. Matching time on the text string of length n is theta of n. Memory uses order of M sigma. Best processing time is order of M sigma. Here we have to we can use a compute transition function to transition function, that is delta, using the PE pattern and the sigma as the input symbol. Running time for the transition function pseudocode is order of M cube sigma. Now finally we have the Morris-Platt algorithm. It is similar to the finite state automaton. Here whenever there is a mismatch of the several characters matched, then the pattern and search string contain the same values. Therefore, we can match the pattern against itself by pre-computing a prefix function to find out how far we can shift ahead. This means we can dispense with computing the transition function altogether. By using the prefix function, the algorithm improves the running time by order of n plus n. Here is an example for the KMP algorithm, and this is a pseudocode for the prefix function, and here for the KMP matcher, taking the text and the pattern as the input. Runtime and the overall complexity is order of m plus n. Here is a comparison for the naive algorithm, Robin curve, and the finite automaton, pre-processing time and the matching time. Thank you.